Equations of tangent lines in parametric curves. That's the subject for today. I'm about to take a look at one of the examples from your note packet, and the focus on this high-tech equipment is not so hot today, but remember that you have it in your note packet. It's also completed, the work of mine is completed online in the lesson plans as well as the blank note packet. But we have this set of parametric equations, so it's defining some curve. It's probably quite curvy, and we're going to say t represents time. At time t equals 3 pi over 4, we want to know the equation of the line that's tangent to that set of parametric equations. So as soon as you hear tangent line, you remember from your first calculus course days, you have a knee-jerk reaction. You want a point and you want a slope. And there is no choice. You need both of those if you're going to build a line. So we need to go ahead and get those. Getting the point is as straightforward as plugging into your equations. So I have an x equation, and I'm going to plug in 3 pi over 4. And I'm going to do the same thing to the y equation. I'm going to plug in a 3 pi over 4. And now I have my xy coordinate. And 3 pi over 4, that's a pesky location on the unit circle. That's for cosine, negative square root of 2 over 2. And for sine, it's positive square root of 2 over 2. Looks like I should multiply by a 3. So, sorry for the sloppiness down there, but I'll write this point very, very nicely. My x-coordinate would be 2 square roots of 2. And my y-coordinate, there it is. I now have a point on my graph at time 3 pi over 4. Now I need the slope at that point. Oh, and by the way, I just noticed at 3 pi over 4, the cosine is negative. To get to that spot, that's a negative cosine, so I needed a negative there, which makes me have a negative there. I'm not on my game today. By the way, very recently I saw a bunch of spike ballers out in the faculty parking lot. I don't know if they were scheming or not, but then I offered them a chance to win a donut by having the first person name a song that I was playing in my car radio. And Nick Coughlin, I hope he has a conscience, because he looked on my car radio's readout and found out that the band was Rush and won his free donut in a possibly unethical way, but I'm going to live up to my word and give him his donut. That has nothing to do with this lesson. We have our point. Let's find the slope. I'm going to pause this and do my work, but before I do that, I'll set it up. If I want my slope, I want my dy dx evaluated at t equals 3 pi over 4, which means I need to go back to my derivative and do a dy dt at 3 pi over 4 and a dx dt at 3 pi over 4. And since you don't feel like watching me write all that stuff out, I'm going to go ahead and pause this. Okay, so I'm back. You still have this lousy focus issue. I apologize. So I'm trying to find the slope at 3 pi over 4 because I already have the point. And what you're going to find out is finding slopes in parametric equations can get quite tedious. So my derivative of my y plugged in at 3 pi over 4, my derivative of my x equation plugged in with a 3 pi over 4 gives me this big mess, but through the miracle of arithmetic reduction, it ends up equaling 3/4. So you see that there's quite a bit of possibility in here for making a mistake. And just a small pro tip, a mistake that is pretty easy to happen. The slope formula says derivative of y on the top, derivative of x on the bottom. But when you look at your parametric equations, how they're given to you, normally x is above y, which makes it really easy to accidentally mix up this order. So just be careful there. All right, so once I have all that work just to get the point and the slope, now I can do my equation of my line pretty easily. there it is. And if I feel like rearranging that, go for it, but there's really no reason. And remember, the form of the line that I'm using is the old y minus y equals m x minus x. It wouldn't hurt you to write that first before you do that, because it only takes a second. All right, that's a clunky problem. We've got one more tangent line problem to do. I'll try to do it quicker. Okay, so I've moved on to the next page in the notes, and I have this new set of parametrically defined curves, or one curve defined parametrically by x and y, and I want to find horizontal and vertical tangents. And what I'm going to need when I do this, first of all, is definitely a first derivative. So before I worry about anything else, I'm going to do my first derivative, and I'm going to pause this while I put this out here. There's my first derivative, and at first you might be disappointed that it's a fraction, but you shouldn't be disappointed, because remember, when your derivative is like a fraction, not like a fraction, when it is a fraction, it offers you some flexibility that you wouldn't normally have. So for example, when a fraction has a numerator of 0, no matter what's on the denominator, as long as that's not a 0, then the final result is a 0, which is the slope of a horizontal tangent. When a fraction has a 0 in the denominator, what you end up with is an undefined result, which would be a vertical tangent. So you really enjoy having a fraction. It makes these calculations a heck of a lot easier. So now if I want to find my horizontal tangent, it's when my fraction of my derivative equals 0, which means it's when my numerator equals 0, and that ends up being t equals 3/2, or 1.5 for those of you who are fans of decimals. So now read carefully, because we were asked to find the point x comma y. We found the time, and sometimes I might ask you for the time or the value of t, but if I want to find the actual point, I need to go ahead and I need to plug in. I put a 1.5 into 1.5 squared plus 1.5. I'm going up to the original equation, and I'm going to put a 1.5 into the y. And I worked that out before. I would get a 3.75 comma 2.75. So I don't necessarily know what the graph of this parametric curve looks like, but I know at that spot on the coordinate grid, I get a horizontal tangent. We haven't even talked about the concavity. All right, so let's take a look at the vertical tangent now. That is when the denominator of your derivative equals 0. So that is this simple equation, and a little mental math gives me a negative 1/2. So now I know that I need to plug in to the actual y and x equations to get my final value. I'm going to skip the tedious work and just go straight to it. Remember that I'm actually plugging into these values, or these equations, not the actual slope values. And I now know that at this spot, I don't necessarily know much more about that spot, but I know right there I have a horizontal tangent. Nope, I misspoke. That's a vertical tangent. Okay, so this has been a very choppy video. Not my finest work, but you now have a good idea of how to either compute a tangent line or how to use a tangent line further in some other applications. See ya.